Today I would like to show you how we can model the optical constants of oxides, and we will be able to use the same model for nitrides as well. So basically for dielectric materials which are more or less transparent in the visible spectral range, maybe they will show a little bit absorption in the ultraviolet, but otherwise they will be transparent. I would like to start with this configuration here that we developed when we were discussing transparent glass substrates, and this was the last fit for the BK7 substrate. And on top of the substrate I have data for deposited oxides, two different types of oxides, one with large refractive index values, the other one with rather small ones. We will see how these materials will differ from each other. So let's first load measured spectra of the coated glass. We can use the import command here to tell code we want to import measured data. We can call this new sample oxide 1 on BK7, and this is the reflectance spectrum, and I have stored it in the so-called XY format, which is a text file with just one column of wavelengths and one column of reflectance values. When we import, code found the spectral range 300 to 2500 nanometers covered by 1101 point. The unit is nanometers, and for the transmission I have a similar data format, and here are the new curves. Basically following with the minima here in reflectance, the curve of the substrate, and also with the maxima of the transmittance. So let's now include a thin film on the substrate in our model. We have to go to the tree view and go to the list of materials first. And in this case, I would like to build up the optical constant model from scratch. That means this time I will not use a predefined model from the database, but I will just use this list of new object types in the list of materials to select a dielectric function model, which will be an object that models optical constant for the new materials, and I generate an object of this type, and I call it oxide 1. And once we have declared this, it's a good time now, a good moment now to set the color. Let's say we pick this one to identify these objects in the graphs and lists that we will be filling now. Okay, let's start with the simplest model of all. Let's start with a constant refractive index. In the tutorial about optical constants, I told you that assuming a constant refractive index is a good approximation in the infrared and sometimes also in the near infrared. So we can try that before we do anything more complicated. If we open the list of materials here in the tree view, the oxide 1 object, the new one, has a sub-object called susceptibilities, and this is a list of susceptibility contributions, basically contributions of terms that describe excitations like interband transitions, vibrational modes, or the acceleration of free charge carriers. So if we open the susceptibility list, it's empty, there's nothing defined yet, and here in the drop-down box we have the choice of different types of susceptibilities, and we start with a very simple one, the constant refractive index. If I generate an object of this type, I usually call this N0 to identify or to make clear this is a constant, and we can give it any value here. Let's say 1.8 would be a good starting value, but we will have to adjust that anyway. If we go one level up, click on oxide, we have to set the range command here, and we should compute the data also from 300 to 2500. Maybe with 300 points would be sufficient. The number of points can be independent of the number of points for the spectral objects. Code is very flexible concerning spectral ranges, but we should just make sure that the minimum and maximum cover at least the range of all the spectra that we want to compute. Pressing OK, we can execute recalc and then press the keyboard character A for automatic scaling, and then you see here the imaginary part, the red curve here is 0, the real part is 1.8. We can show this material here in the view. You can probably remember from this section about the user interface how we can do that. We can open the list of view elements. That's still the object called start screen here, and we drag and drop the oxide 1 object here. Then we can press F7 and rescale with the Shift Alt command the new object here in this main view. Okay, now let's go to the layer stack. Here we still have only the glass. So if we go to the tree view, open the layer stack, we can generate on top of this glass layer, we can generate a thin film. Drag and drop oxide 1 to this thin film, and so we have 100 nanometers of this oxide 1. Then let's go to clean up the list of fit parameters, which is here. This still contains the fit parameters of the BK7 model that we adjusted, so let's delete all of them. The substrate is now fixed, and generate a new set of fit parameters. Actually, I want to vary the N0. That's the constant refractive index that we have used for the optical constant model, and holding the control key down, I will select also the oxide 1 layer thickness. Then press OK, and just set some boundaries. The lower limit for the constant refractive index should be 1, the higher limit, let's say 5, and maybe the thickness should be flexible between 0 nanometers and 500. Press F7 and verify that we now see different blue spectra, and the spectra depend on the thickness. I vary the thickness now, and maybe you remember a discussion of wave propagation in thin films. The maxima here, they will mainly depend on the N0 value, on the height of the refractive index. If I make this large enough, we can get almost here the same height as in the measurement, and with the thickness we can adjust the phase basically, and you can see here already in the near infrared the assumption of a constant refractive index with a certain thickness is not too bad. But obviously here for the blue end of the visible and the ultraviolet, we need a higher value for the maxima. That would mean here in that case we need a higher refractive index. So 2.6 would be good instead of 2.27 here. So the refractive index should be higher for smaller wavelengths, and maybe remember we have called that normal dispersion. So which is normal. Actually, what we could do now, fit the model automatically. It doesn't really lead to a nice agreement because the optical constants of this material are not constant, but they show some variation. So let's introduce some variation. Let's first introduce a little bit of dispersion by adding a simple harmonic oscillator very far in the ultraviolet, and that can represent high energy interband transitions, and we can simply try if that can help us already to get a nicer match. So let's go to the tree view once more, open the list of susceptibilities of this oxide 1, and generate an object of type harmonic oscillator. We can call this UV, just to remind us that this will be an ultraviolet excitation. Ultraviolet means a wavelength smaller than 400 nanometers. Actually, here for oscillator models and for almost all models for susceptibilities, the parameters that we have to enter are have the units wave numbers. For historic reasons, the resonance frequency of this oscillator should be in the ultraviolet, and that means, for example, something like 60,000 wave numbers. The oscillator strength, well, we don't really know what is a reasonable number. I can tell you something like 50,000 could be okay, and the damping constant should be very small. We don't want to see any absorption of this oscillator. We just want to see the dispersion that is generated by it. So we have to make it very narrow to avoid that we really see absorption. Good. Now we can take a look at oxide 1 here at the optical constants. Press A for automatic scaling. Maybe I should also press recalc and press A again. So this now looks a little bit more realistic. The refractive index, the real part here, shows dispersion. That's what I wanted to achieve. And we can now go to the list of fit parameters and add one more parameter. Actually, we should add the oscillator strength of this UV oscillator. This number here. We can keep the resonance frequency and the damping constant. We just want to make sure that we can make the interband transition stronger or weaker with this parameter. Okay, so now we should also have a variation of the parameter, let's say between 0 and 200,000. So we can now see what happens if we change this value. We can also make the constant here smaller then. And actually what we can do now, we can just press start and see what code gives us automatically with the automatic adaptation of the model. We can be a little bit better now between the infrared and the ultraviolet, but still, of course, it's not perfect because obviously there is some absorption here, which is not the absorption of BK7 substrate, but this steep decrease here of the transmission towards the ultraviolet, that must be caused by the thin film. It was not present in the BK7 data already. So we have to introduce an interband transition which is closer to the visible, and in order to describe details of this absorption. So that would be the next step, to introduce an interband transition model which can realistically describe the shape of K and the real part here for an absorptive excitation. Actually, as it turns out, we can introduce realistic interband transitions only with the help of an additional mechanism. I will show that in a moment. Actually, the mechanism is called Kramer's chronic relation, and this means we can relate the real and the imaginary part of optical constants. They are related by a physical relationship, which is known as Kramer's chronic relation. And we need that here because good models for interband transitions are usually delivered or developed by doing some quantum mechanical computations, and they end up in absorption coefficients usually. Basically, you can turn that into an imaginary part of the refractive index, but unfortunately there's no mathematical expression then for the real part. So the real part is unknown, and we have to reconstruct it from the known imaginary part, and that is done by the so-called Kramer's chronic relation. Fortunately, there's a way how to do that rather fast with the help of computers. You can do the Kramer's chronic transformation from the imaginary part to the real part by performing two fast Fourier transforms. Basically, you take the imaginary part in frequency space, you do a Fourier transform to the time domain, you do some manipulations which are based on a principle called causality that puts some restrictions on the response function in the time domain, and then you transfer back to the frequency domain by a reverse Fourier transform. And then you have the real part and the imaginary part. And I have implemented a susceptibility object that does exactly this, that does the reconstruction of the real part. And this object is called KKR susceptibility. And we have to define and declare all interband transition models inside this KKR susceptibility. So first we select this type, press plus, give it the name IB for interband transitions, and then we have to open this object here in the list of susceptibilities, the IB object. In fact, it has a sub-object called KKR reconstruction. We will take a look at this in a moment. And this object, interestingly, has another sub-object also called susceptibilities. And here, that's the list, which is empty still, where we can define now interband transitions models. Actually, here you have the choice between those four different types. Usually, I prefer to use either the Taug-Lorentz model for crystalline materials or the OGL2 interband transition model, which I developed based on a publication by some authors. And the names of these authors are abbreviated OGL. So this object type is generated. I give it the name just OGL. We will just have one of these objects necessary. So once we have declared that, we will take a look at the parameters when we select them as fit parameters. Let's first go to the KKR reconstruction object. That's a window like that. If we execute the recalc function and press A for automatic scaling, you will see here the imaginary part of the refractive index generated by the OGL model for a huge wave number range. And here you can see the reconstructed real part. That's what we will use for our modeling. All the settings here are more or less reasonable. We do not have to change them usually. So we can close this window and close this KKR reconstruction subobject, and now take a look at the oxide 1 optical constants. And as you see now here, we now have some absorption generated by the OGL model and also a different shape of the real part. So let's see how far we can get now with this OGL model that we have defined in addition to the constant and the UV oscillator. Let's go to the list of fit parameters and add some more. Actually, here in the oxide 1 section, we have 4 new fit parameters called strength, gap energy, gamma, and decay. And we can select the first 3 by holding down the control key. The decay parameter usually can be kept fixed for a moment, but we should make these 3 flexible. Gap energy basically is the gap energy, the distance between the valence and the conduction band. The strength is the overall strength of the transition, something like the square of matrix elements in quantum mechanics. And the gamma value, that basically is a value which is sometimes called the disorder parameter, and it measures basically how disordered the material is. In the case of amorphous sputtered oxides or nitrides, this gamma value just more or less means how developed is the microstructure of the material, from completely amorphous to maybe nanocrystalline or even microcrystalline. Something in between. If you have something in between, then you can express that by a gamma value, a certain gamma value. Okay, let's declare these values and put some ranges here, maybe 0 to 10 for the strength, the gap energy from 0 to 50,000, that's also in wave numbers, and the gamma value from 0 to 10,000, that's also measured in wave numbers. So let's press F7, and you can see already here that we now have strong absorption. Here the reflectance is below 30%, the transmission goes to 0. So here we have 70% absorption, and you can see that the decay of the transmission here depends mainly on the gap energy. So if I change the gap energy to higher values, we can match basically here the measured curve in this area. Actually, we can. We're almost ready to start the automatic fit. I guess there's no need to do further manual variations. We can just press start and watch if code will be able to adapt the model to the measured data. And actually that works very nicely. Okay, actually we can press the keyboard command S to see the status bar here. The status bar gives us some information about the progress of the fit. In particular, it gives here the fit deviation, which is the mean square difference between the red curve, which is the measured spectrum, and the blue curve, which is the simulated one. So these numbers are very small, so the mean square deviation is also very small, and that means the fit is okay. The only problem that we have here is this difference in the near infrared. At this point, We could add some oscillators there, but I'm not really sure if this is due to the thin film. It could also be that here we have a little bit stronger absorption of the glass. So I'm not absolutely sure that this is due to the thin film, so we will not work on this for the moment. Just look at values below 2000 and be happy. That's a nice fit. Actually, it's a very good fit. So we, at least below 2000 nanometers, we know the refractive index values very nicely at a very high quality, and the thickness is also determined very accurately. Okay, that's very nice. We can save this result, and we can press the key M so that we have the menu here. Then we can use the command File Save As to go to the right folder where we have the oxides on BK7, and we can call this oxide 1 fit. Okay. Actually, what you should do now in serious work, you should store the new optical constants. We now have determined the optical constants of oxide 1, and we should store those to the database. Let's do that now. Press F7. Go to the list of materials, and we can call the oxide 1. Well, we can give it the name video tutorial oxide 1, and then we can store this to the database of optical constants, which is here in the tree view. If we open that with the right mouse click, you probably remember from one of the previous sessions that we have a list here of predefined materials, and we can now drag the video tutorial oxide 1 object to this list. Code will ask you which is the object file format, the file version basically. Let's store it with the current version, the latest version of code that I'm working with right now. That would be version 4.55. I should leave my initials here so that everybody knows who is responsible for this item in the database, and I could place a comment here: obtained by fit to R and T spectra. That leaves some information about the origin of these data. Actually, we could also rename the BK7 model to, we can rename that to video tutorial BK7, and then store that to the database as well. So if we drag and drop this, same action, this was the float glass model adapted to R and T values. Okay, now we have stored both optical constants that we have, optical constant objects that we have developed up to now. Let's make another example. We have loaded here spectra measured for oxide 1. I have a second set of reflectance and transmittance spectra measured for a different type of oxide. And I will now show you that we can use exactly the same model also for the second oxide. Let's use the import command here once more, and name the new sample oxide 2 on BK7, and I have spectra of oxide 2 here also. And you can see only a very small variation. So actually what we can see here is the optical, the spectra are not very different from the spectra of pure BK7 without any coating. So that already can tell us that the oxide 2 material has refractive index values which should be very close to the ones of BK7. Let me first rename this object. Rename the video tutorial oxide 1 object to video tutorial oxide 2, and then do some manual adjustments. Actually, we have to move the gap energy to higher energies to avoid the strong absorption. Actually, we have to make the strength of the transition also small, and probably also the N0 value here should be smaller. So now if I tune this more or less carefully, we have in between a situation where we don't have any structures here, any interference pattern. Now we have defined optical constants which are almost the same as BK7. And if we go to smaller values, you can see that the minima here now go down below the level of the substrate, of the pure substrate. So we can increase now the thickness and get a rather good agreement here already almost everywhere. So let's now do the rest by the automatic fit. Press start, which should be a kind of piece of cake in this case because we were already very close. So now the refractive index value is varied a little bit below the level of the BK7 glass, and that seems to work also quite nicely. And note that we use here 5 parameters for the optical constants, and 1 parameter is the thickness. So as long as you have single layers of oxides, sputtered oxides, or otherwise the permanent deposited oxide layers or nitrides, that should always work using this model. I have very good experience applying this model to all kinds of materials. And so now we are finished with this material. We can save this material also to the database. So if I drag and drop this model, and then we should also store this whole configuration as file, save as oxide 2 fit. Okay, this method you can use whenever you have materials which are close to, which have optical constants close to those of glass, and you can use the method that we have adapted previously, the oxide 1 fit, when you have a large contrast between the thin film and the substrate, because the refractive index values here are really very different. So this would be the ideal model to start with. If you have titanium dioxide or tin oxide, then you can start here, adapt the few parameters only, and then you should be good. Okay, as a follow-up of this tutorial, I will generate one where we repeat some of these steps, but in a limited spectral range, so that we can analyze a lot of input spectra that have been measured in the factory, as basically analyzing a series of spectra obtained by a traverse system in a large area coater. And the goal there is to get the thickness profile of the layer and the change of the optical constants versus position. And I will show that in another tutorial how to do that in a batch operation. But for today, that's enough, and I would like to thank you for your attention.